Precision. Precision is a word we use that tells us how closely repeated measurements agree with one another, right? But accuracy actually talks about how closely repeated measurements agree with the true value of whatever it is you're trying to measure. So I've underlined the relevant words. True value applies to accuracy. That's what we typically think of when we think of accuracy and precision in everyday life. We think about how true it is. But actually, precision has nothing to do with that. Precision is just talking about if you take 5 measurements in a row of some temperature or something, or 5 measurements of the thickness of a human hair, that all 5 measurements will agree with each other really closely. And the closer that repeated measurements agree with one another, like if I take 10 measurements, if they all agree with each other very closely, then we say that the measurement was very precise, or the instrument, the scale or the balance or the thermometer, whatever, was very precise. But it's only accurate if these closely repeated measures agree with the true value of what it is you're trying to measure, the actual mass of whatever it is you're trying to do. So accuracy relates to truth. Precision doesn't have anything to do with truth. It just talks about how repeated measurements agree with each other. Now, the good news is it's very easy to understand this. And we're going to do it like this. Here, I'm going to draw a dartboard. So here is a dartboard, right? And then in the middle here is another dartboard. And over here is a third dartboard. They're all identical situations. Now, right in the center of the dartboard is the bullseye. This is what we consider, I guess, truth, right? The bullseye is trying to reach truth. In other words, usually in science, you're trying to measure something. You know, what is the density of this thing? And what we calculated, is it closely related to truth? Because that's what you're always trying to get, the truest value you can. So the bullseye here represents being right on the money, exactly as close to the true value as you can. Now let's consider a couple of scenarios. Let's say that I take the first measurement of whatever it is I'm measuring and I get very close to the true value. That's what the X is. That's a dart I've thrown here at the dartboard. And then I take a second measurement and I don't land right on top of the first one, but I land very close, but also close to the true value. And then I make a third measurement and I'm also, again, close to the bullseye, close to the other guys here. Now that's 3 measurements, but I might actually make 15 measurements or 25 or 1,000 measurements or whatever it is, okay? Now, because all 3 of these measurements, darts in this case, they agree with each other because they're all closely spaced, very close to each other. The blue X's are very close to each other. That means that we have very high precision, right? But because these measurements, these darts, are also close to the bullseye, close to the true value, we also have very high accuracy. So when you take multiple repeated measurements, this is what you want. You want the multiple repeated measurements to be close to the adjacent or subsequent measurements, but you also want those measurements to be close to truth, as close as you can. That's what you want, right? So that's very high accuracy and high precision. Now let's take another situation. Let's say I throw a dart or take a measurement and I land up here someplace. And then I take another measurement and I land up here someplace. And I take a third measurement and I land down here someplace. Notice that all 3 of my measurements, or my darts, they're all clustered, very close, very repeatable, right? But they're nowhere close to the true value. So because they're not close to the true value, we actually have very low accuracy. Because accuracy relates to truth. How close am I to true? But I'm not anywhere close to true. However, I have very high precision. This is a situation most people don't have any idea can happen. You normally think accuracy and precision are both the same, but they're not. Because if you have measurements that are all closely related to each other, or closely, you take one after the other and you're getting very similar numbers, you think that's good. But what if they're all wrong, right? That would be an example of a scale, like a balance, and somebody goes underneath the balance and just glues a weight on the bottom of the balance. You can't see it, right? So all of the measurements of the balance are going to be very heavy. They're going to be heavier than truth because somebody glued like some kind of weight underneath it, right? But because the balance has a constant weight every time, all of my measurements, one after the other, they're all going to be very close, but they're all going to be wrong. So I'm going to have a very low accuracy, but a very high precision. Now let's take a look at the last case. Let's say I take my measurement, first measurement lands over here, next measurement lands somewhere over here, third measurement lands somewhere down here. So Because all of the measurements are nowhere close to truth, I have a very low accuracy. And also all the measurements are not anywhere close to each other, I have a very low precision as well. This would be the worst case situation where you're taking measurements and they're all different from each other and they're all totally different than what I think the true value should be close to. Then I don't have any idea what's wrong with my experiment, but you got to fix something. So these are the three cases. If you have clustered measurements that are all near truth, high accuracy, high precision. If you have clustered measurements, which are all far away from truth, like the scale balance with somebody that glued something on the bottom, low accuracy because it's not anywhere close to truth, very high precision because it's very repeatable. And then when you don't have any repeatability and all of the things are very far from truth, we say low accuracy, low precision. All right, I want you to remember this picture because that picture will explain accuracy and precision 5 years from now if you forget. This picture will be what you need to remember to help you remember it. All right, now that we have the idea of accuracy and precision out of the way, we need to talk more about measurements. You see, in chemistry and also in physics and any other science, we have some numbers that we trust 100%. We call them exact numbers. And I'll give you examples in just a second, but we also have numbers that we have some confidence in, but we're not totally sure how true they are. And those are going to be basically anything you measure. Anytime you measure something and you do 2 or 3 repeated measurements, you're going to get very slight differences in the measurement. Even if you're very precise, even if you're very, very careful, you're going to get multiple repeated measurements that are slightly different because nothing is ever totally repeatable here. You could have a power surge in the walls powering your equipment, or air currents in the room affecting your balance. Anything can happen. Somebody could be stomping down the hallway affecting your experiment. So subsequent measurements are never exactly the same. So we call those measurements, they're not exact. But let's talk about the difference between exact situation and other situations. So we have this thing called an exact number. An exact number. There are numbers that you would, there's not going to be any surprises here. But for instance, if I told you I have 12 eggs, you would assume that's an exact number. I didn't really have to measure the eggs. They're whole objects. There's absolutely no chance that I miscount. I mean, there is a chance, but repeated measurements of the box of eggs is always going to give you 12 eggs. There's no way you're going to get that wrong. It's an exact number because a dozen eggs is defined to be 12 eggs, right? If I go out in the park and I count 5 rocks, this 5 is an exact number because I count them 1, 2, 3, 4, 5, and I'm going to count 5 over and over again. I'm never going to be wrong. Measuring rocks is not like measuring volume. I mean, you know when you have 5 rocks, okay? So it's an exact number. Also, conversion factors are exact. So if I tell you there's 1,000 grams in 1 kilogram, right? The 1,000 is an exact number, and the 1 kilogram is an exact number because it's set up to be an exact conversion factor. So I don't have to worry about the significant figures we're going to talk about in a minute in these numbers because they're defined to be exactly this. So they're an exact number. One more example, it's defined to be exactly 2.54 centimeters in 1 inch. I know we don't use inches too much here, but this is a conversion factor with a decimal point. It doesn't have to be whole numbers. But this is defined to be exact. Not 2.54302, it's 2.54, and that's it, it's exact. So when you're doing calculations that involve exact numbers, you don't have to worry about if those numbers are significant figures or measured figures. You calculate with them, but you don't round your answer based on any of these whole numbers. Because the 1 inch here, if you put that into a calculation, you wouldn't round your answer to 1 digit just because you use 1 inch. That would be silly. You wouldn't round your answer to 3 digits because there's 3 significant figures in the 2.54. You wouldn't do that because that's an exact number. It's exactly 2.54. There's no uncertainty in these numbers. All right, now let's talk about the situation when we don't have exact numbers. Not exact numbers are basically all measured. All measurements. Anything you measure is not exact, as I talked to you about before. And I'll give you a good example of that right here. Let's say that I have some thermometer, right? And on there, this is marked to be 30 degrees Celsius, and this is marked to be 25 degrees Celsius. and I would like to make a measurement. If I have the liquid level in the thermometer right here, I know it's exactly 25. If I have the liquid level right here, I know it's exactly 30. But what about if the liquid line is right here? What temperature is this? Well, I think it's about 27 degrees Celsius, but is it 28? Well, it's probably not 28. I can probably guess pretty close that this is 27. So 27, 26, 27, 28, 29, and 30. So I'm pretty confident it's 27. However, I would never, ever, ever say that it's like 27.3 degrees Celsius because you can't read that level of detail here. So you would never say that. You would never say it's 27.6, 2, 3, 4, 9, or 6, 7, 2 degrees Celsius. You wouldn't say that because there's no way we can read a measurement like this and get anything like this. So we know that we can't do things like this. Clearly, if you take a measurement and you put too many digits on the end of it just by reading it, it's going to mean nothing. It's going to be nonsense. There has to be some way to quantify what and how many of the digits in your measurement are what we call significant. The significant digits are the ones we're sure about. But if you take the measurement too far out beyond what your instrument can do, then you're just not sure of those. And we say that those are not significant. We don't really use those or don't trust those digits in the calculation, basically. So in the rest of this lesson, we're going to talk about how to look at numbers and how to determine how many of the digits are significant in there. And there's some rules we have to learn. So this lesson is all about just counting significant digits. And in the next lesson, we're going to talk about what do you do when you calculate with significant digits. But I'll give you a roadmap. What we're going to do is learn how to count significant figures in the numbers. And then later when we calculate, we're going to get our answer and we're going to determine where to round the answer based on the significant figures in the numbers that we started with. Because you can't have like 34.1 grams or whatever and 27.2 grams and do some calculation. You can't get an answer of 44.6972311 blah, 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 blah. You can't get so many digits in your answer when you only had like a fixed amount of digits in the numbers that you started with, because that is just too many digits representing an accuracy to truth higher than my original numbers actually had. So you have to figure out where to cut it off and where to round it, and that's what significant figures are really for. So let's talk about significant figures. All right, the rules look like they're hard, but actually they're not. Okay, let me show you the easiest way I know. Okay, if I give you a number, so I'm going to put like a little arrow here for the first little rule. If I give you a number 1342.6, this has 5 significant figures. 1, 2, 3, 4, 5. The first rule, I'm not even going to write this rule down, but the first rule is any non-zero number, like any number 1, 2, 3, 4, 5, 6, 7, 8, or 9, they're always significant. So there's no zeros here. Now there is a decimal, but decimals are fine. Any number that you have that's non-zero, it's significant. 1, 2, 3, 4, and then 5. 5 significant figures. Bam, your first rule is very simple. Any non-zero numbers you see, they're always significant. Now let's take a look at rule number 2. What if I give you the number 1005 or the number 7.03? All right, well, this guy actually has 1, 2, 3, 4 significant figures, and this guy actually has 1, 2, 3 significant figures. So the rule here, obviously the non-zero numbers are significant, but what do you do about the zeros? So basically, zeros between numbers are also significant. This is my little shorthand way of saying zeros between numbers are significant. These zeros are between non-zero digits, so they're significant. The decimal doesn't matter at all. This zero, because it's sandwiched between two numbers that are non-zero, it also becomes significant, okay? And when you measure something to 2 digits like that, you have a reasonable assurance that you're making a more accurate measurement, closer to truth. The more digits you have, the more you think you're getting closer and closer to the true value of whatever it is you're measuring. So any zeros between non-zero numbers like that are significant. All right, let's take a look at the next rule. Next rule, what about 0.02 or 0.0026? Now, what do you do here? Here we have zeros, but they're not sandwiched between non-zero numbers. I mean, we have leading zeros, in other words. These are leading zeros here. So actually, this guy has only 1 significant figure. And this guy has only 2 significant figure. And the rule that you follow here is ignore leading. zeros, leading zeros. All right. And what I mean by when I say ignore is they're not significant. So this 0 and this 0 are not significant because they're just padding the front part of the number. This 0, and this 0 are not significant because they're just padding the number. And the reason that you know that you shouldn't count them is because think of the number 5. Number 5. Let's just go over here. 5 is just one significant figure. But you know from the number system that I can actually write this as 0, 0, 0, 0, 0, 0, 0, 0, 0, 5. I can put as many leading zeros as I want, and none of them matter. Only the 5, because all of these are like, this is like the tens place and the hundreds place and the thousands place and so on, but they're all 0. They don't have any value. They don't do anything. They're basically just showing you they're showing you where the decimal goes for the number. Same thing for any zeros that are after the decimal point. They're only showing the position of the decimal. These zeros are only here to show me that these two numbers are worth less in the number. They don't serve a function other than to pad the decimal point. So ignore all leading zeros, one significant digit, two significant digits like this. All right? And this is the only rule that I think is a little confusing to people. Let's give an example, 0.0200 and 3.0. How many significant figures are in these numbers? Well, we already said we're going to ignore leading zeros, so we're ignoring these. This one's significant, but it turns out that trailing zeros, like this one, they are significant if there is a decimal point. So this actually has 3 significant figures. And trailing zeros, like this one, is also significant, assuming there is a decimal point. So there's 2 significant figures here, right? So I'm going to write down here, trailing zeros are significant if there is a decimal point. All right? So this is significant, and this is significant as a trailing zero, only because there is a decimal point. This one, same thing. So that leads us to kind of a bonus situation. How would you tell me the number 10,300? How many significant figures would there be? Well, this is significant, this is significant, this is sandwiched between them, so because of the other rule, it's significant, so there's 3. But I just told you the trailing zeros are only significant as if there's a decimal, and I'm going to tell you right now, there's a little bit of ambiguity. Different books and different authors teach it a little different. So I'm teaching you, what I consider to be the majority of how people use. But there's a little bit of fuzziness. Some people do different things. But in general, trailing zeros are not significant when there is no decimal point. So we don't really count these, and we say there's 3 significant figures. Some people will count this as 5 significant figures, but generally you should only count the zeros that are sandwiched, the non-zero numbers, and we ignore trailing zeros unless there's a decimal like there was up here. So this leads to ambiguity. Some people will say 3, and some people will say 5. So we can ignore this by writing scientific notation. We can write this number as 1.03 times 10 to the 4. When you see scientific notation, you ignore, for the purpose of significant digits, the power, the 10 to the 4. You ignore that, and you only look here. 1, 2, 3 significant figures. This one is sandwiched, so there's 3 significant figures, right? But I could also say, what if I say 1.030 times 10 to the 4? How many significant figures is this one? 1, 2, because it's sandwiched, 3, and then this one's a trailing 0 with a decimal, so there's actually 4 significant figures here. And also, I can say 1.0300 times 10, again, to the 4. These are the same numbers. I'm moving the decimal 1, 2, 3, 4. It's giving me the same number in every case, but up more and more significant figures. Here, there are 5 significant figures. 1, 2, because it's sandwiched, 3, and then the 4, 5 also count because there is a decimal, and the trailing zeros are there as well. There is no way to get good at counting significant figures other than to just solve problems. So right now we're going to switch boards and we're going to solve a bunch of significant figure problems. All right, for the first problem, I'm going to write down a little scenario. We're going to talk about it, and I want you to tell me, is it an exact measurement or not an exact measurement? The first one is the mass of a 2 by 4 inch index card. Is that exact? Or the mass of that card? We're talking about the mass of it, the mass of a 2x4 card. Is it exact or not? Well, it's not going to be exact because there could be very small tolerances in the thickness and things like this of one of these cards, so it's not exact. It would be something you would have to measure, right? But problem number 2 is the number of ounces in a pound. Well, the number of ounces in the pound is not something you measure. It's given to you. It's a defined standard. It is exact. Part C. The volume of a large coffee. The volume of a large coffee. Well, that's a measured quantity. If you take 2 of them, there'll be very slight differences, so that's not an exact quantity. And then we have D. D is the number of inches in a mile. The number of inches in a mile. That's an exact figure. You could look up an exact conversion factor between the number of inches that go into a mile, so that's exact. Okay? E, the number of microseconds in a week. Now, first you might think that that's exact, but actually if you think about leap year and things like that, the length of the days and stuff changes a little. If you're talking about microseconds, it can change. So actually that's not exact. And then finally we have part F, the number of pages in your favorite book. Technically you have to measure it, but you're never going to get it wrong. Repeated measurements will always give you the same thing because they're printed on there, so that's an exact number. All right? Now, we want to start the process of understanding significant figures. What we want to do for these problems is I want you to only look at the zeros in the number and tell me which of the zeros are significant. So what we're going to do is underline the zeros that are significant. All right? So the first number, 0.041. Which of these zeros, if any, are significant? Well, we said leading zeros are not significant. We said right here, ignore leading zeros. Leading zeros, not significant. So that's not significant. That's not significant. So we have nothing to underline. We'll say none of those zeros are actually significant. Okay? Next problem, 0.0410. Which of these are significant? Leading zeros we ignore, but trailing zeros are significant if we have a decimal. Trailing zeros are significant if there is a decimal point like these. And so that one is significant. All right. Next, part C. We have 0.04100. Which of these are significant? Well, again, leading zeros we ignore, but trailing zeros, if there's a decimal, are significant. So both of these zeros are significant. All right? And then finally, I'll go over here for part D. Part D is 4.010 times 10 to the 4. We only look at the first part. We don't consider the 10 to the 4 for scientific notation. This is sandwiched, so it counts. So that one's significant. And this is a trailing zero with a decimal point, so it also is significant. And so we actually have both of those zeros, both of those zeros are significant. All right. So that was just identifying zeros. Next, we're going to write down some numbers, and we're going to state how many significant figures each of these numbers contain. So for part A, 6.070 times 10 to the minus 15th power. How many significant figures does it have? We ignore this. Sandwiched zeros are significant and trailing zeros are significant with a decimal. So 1, 2, 3, 4 significant figures. 4 significant figures. Right? Part B. 0.0038400. How many significant figures do we have? Leading zeros are always ignored. So these are nothing, but we have 1, 2, 3, and these count for 5 because they're trailing zeros with a decimal. So here we have 5 significant figures. Okay, C. We have 17.000. This is significant, this one, and all the trailing zeros are because there is a decimal point. So there's a total of 5. 5 significant figures. All right, next problem, part D. 8.0 times 10 to the 8th. Both of them are significant because this 0 is trailing with a decimal, so there's actually 2 significant figures here. All right, let's move along over here to E. Let me just double check. Yeah, E. 463.805. How many significant figures do we have right here? 1, 2, 3, 4, 5, and 6, because this is sandwiched between them. So there's 6 significant figures right here. All right, F. F is the number 3,000. How many significant figures? Now, if you knew this was an exact number, you would just say that, you know, we don't even have to consider the significant figures. But assuming this is a measurement, there's only one significant figure because the trailing zeros don't count unless there's a decimal point, and there isn't. So that one only has one significant figure. G. G is 301. And how many significant figures do we have? There's 3 of them right here because the 0 is sandwiched, so it counts. And H, E, F, G, H. H is the number 30 with a decimal at the end. Notice I didn't put 30.0, I just said 30 with a decimal. That is a significant figure. This one counts because there's a decimal point. Even though there's nothing else there, because there's a decimal point, it counts, so there's 2 significant figures. All right. Now, in the next problem, we're going to round to 5 significant figures. 156.852. How do we round to 5 significant figures? Well, this is 1, 2, 3, 4, 5. We want to round this guy, and the next digit is a 2, so anything smaller than 5 is going to go down, so 156.85. 156.85. All right, next. We have 156.842. How do we round that to 5 significant digits? 1, 2, 3, 4, 5. The adjacent guy, again, is less than 5, so it's going to be 156.84 because that was the number in that position, 0.84. Part C is 156.849. How do we round that to 5 significant digits? This is the 5th one, so we're going to round, since the next one over is 5 or greater, we're going to round this up to 156.85 because then the 4 turns into a 5. And then finally, for our last one, we have 156.899. So the 5th position is here, and it's a 9. The next one over is going to flip it over, so this has to roll over to a 90. So 156.90. And notice that this is significant because it's a trailing 0 with a decimal, so there's still 5 significant figures in this answer. All right. Now, what we want to do for our very last problem, this is the very last problem, is we want to, for the following values, we want to round them to 3 significant figures, and then we want to rewrite them in scientific notation. So we're going to round them first, then we're going to write it in scientific notation. So for part A, we have 102.53070. Want to round it to 3 significant figures. 3 significant figures is just right here, essentially. So because this is significant because it's sandwiched between, and the next digit over is a 5, so this rounds up to a 103. That's 3 significant figures. How would you write this in scientific notation? You write it with a decimal after the first number, and then you got to move that decimal 2 positions to the right to make it 103. So 1.03 times 10 to the 2. Right, next problem, same exact direction, 656.980. Want to round it to 3 significant figures first. This would be right here. The next one over is a 9, so that kicks it up to a 7 right here. 657, that's 3 significant figures. How do we write that in scientific notation? 6.57, we just put the decimal there, and then 10 to the 2 kicks it over to the right. 6.57 times 10 to the 2. Next problem, I only have a couple more. 0.00854 3210. Okay. So what do we have here? 3 significant figures. All of these leading zeros are non-significant. So we start counting here. 1, 2, 3. We have to round this, but the next one is less than 5, so it stays 854. 0.00854. Basically, it becomes unchanged because we're rounding down, essentially. How do we write that in scientific notation? We put the decimal after the first non-zero digit, 8.54 times 10 to the what? If it's here, it has to go back 1, 2, 3. So 10 to the minus 3 to move it backwards. So 8.54 times 10 to the minus 3. All right, almost done. Only 2 more of these. We have 0.000, then a 2, then a 578, and then 578, and then 70. We're going to round this guy to 3 significant figures. These leading zeros, none of them are significant. So 1, 2, 3, we're rounding this position. The 8 makes this 7 turn into an 8. So 0.000258. This 7 turns into an 8 because the next door was 5 or greater. All right, and then to write this in scientific notation, the decimal goes here, 2.58 times 10 to the what? If the decimal's here, it goes backwards 1, 2, 3, 4. So to the minus 4 power. And our very last problem, I know it's been kind of a long lesson, it is negative 0.03 57202. 57202. All right, 3 significant figures. Again, leading zeros don't count, so we start counting right here. 1, 2, 3. The 7, the next door neighbor is less than 5, so it stays as a 7. So we have negative 0.0357. And to write that in scientific notation, we make it negative 3.57 times 10 to the negative what? If the decimal were here, it goes backwards 2 positions. So it's a negative 2. Negative 3.57 times 10 to the minus 2. So in this lesson, we have learned a tremendous amount. We learned about accuracy. We learned about precision and measurements. We learned about significant figures and exact numbers. And then we learned how to count significant figures. And we did a ton of practice to get the idea of how to count and know which digits are significant. Now, follow me on to the next lesson. We're going to learn how to calculate and how to arrive and know where to round our answers by knowing the significant figures in our problem. Learn anything at mathandscience.com.